Hello and welcome to week 12 of the course on model predictive control. In this week, we are continuing with our description of model predictive control. In this particular lecture, let me recap some of the most important points of linear MPC, some key features and results. Again, when we say MPC, we now mean primarily state space MPC. So I'm not going to use state space based MPC from this point onwards. We'll use the term MPC to represent state space based MPC and dynamic matrix control or DMC to represent step response based MPC. Okay. So let's recap what we talked about components of MPC. Right. So what I'm showing over here is at the current time k, we have the system that has moved in a particular way in the recent past, and the past is covered by these output moves and this input moves in the past. We use a model in order to determine bunch of input moves in the future, and we predict what the output is going to look like in the future. Okay, we use an optimizer in order to find the best set of m input moves in the future so that the system is driven to the set point as quickly as possible. Okay, now what we do is we implement this in a receding horizon manner, which basically means that we throw away the future calculations. We only implement the current input move at time k. Okay, and because of the implementation of current input move at time k, the system responds, and this is the way the system has responded. Okay, as you can see over here, the system's response and our model's predictions are not exactly matching. Okay, there is a difference between the two. Why could there be the difference? The difference could be either because of model plant mismatch, which means the model does not exactly represent the plant behavior, or it could be because of the presence of unmeasured disturbances. Either of the cases, there is going to be an error that is going to be persistently present in the overall predictions, and that error needs to be corrected. That is what I meant when I had used the term we need to ensure an integral action in MPC. The more technically appropriate term for this is that we need to ensure MPC design such that it guarantees offset-free control. Okay, what we offset free control, which the thing that we use in PI controller in order to ensure offset free control is basically the integrator. What we do in state space MPC, I'm going to talk about in this particular lecture. This is something that I have discussed in the previous couple of weeks, but because of the importance of this topic as well as some confusion that questions that I received from students, I think it's a good idea to spend this particular lecture on recapping that. But before we go and speak about offset-free control, let's talk about the various components of MPC, something that you are very familiar with because I have spoken about it multiple times in this particular course. Okay, the first component is dynamic process model, and in this week we are talking about MPC, which uses state space model. Okay, we build a multi-step prediction equation in the form of yp k plus 1 given k, which is in response to the input moves delta um k, which means basically we are going to predict yk plus 1, yk plus 2, yk plus 3 up to yk plus p using the input moves uk plus 1 up to uk plus m minus 1. Okay. The objective is the quadratic objective function, which is summation over the prediction horizon y minus y set point transpose q y minus y set point plus summation over the control horizon delta u transpose r delta u. Okay, and then the constraints is something that we have not spoken about since week number 7 at all, and constraints is one of the most important parts of MPC. Okay, the constraints that we are talking about is input constraints, input rate constraints, and output or state constraints. Okay, the next is the optimization solver. The optimization solver the problem that we are going to solve is a quadratic programming problem, In week number 6, we have used a solver in MATLAB called QuadProg. The MPC toolbox also uses a similar type of a solver, though not necessarily QuadProg. Okay, and the state update scheme in DMC algorithm, we had y tilde k plus 1 equal to m y tilde k, which is just a shift operation, plus sx delta uk plus sd delta dk. Okay, instead we are going to use our filter or our predictor in order to use the state update scheme. So we are going to use the Kalman filter or any other observer. Okay, an observer that is particularly popular, though although I have not talked about it in this course, is what is known as a moving horizon estimator. Okay. And those of you who are interested, I very strongly recommend that you do a literature search or a Google search on moving horizon estimator. There are quite a few good resources that are available. Again, this is if you're interested from your own understanding or from research perspective. Okay, these are the various components of an MPC algorithm. Okay, so let's pick up the components one by one. So let's talk about the state space model. We have spoken about it multiple times. It is xk plus 1 equal to axk plus buk plus bddk, okay, and yk equal to cxk. Okay, now in addition to that, we are going to have possible disturbances. Okay, for offset-free tracking, in order to get rid of the effect of disturbances, you might consider adding a noise component, which could be DE multiplied by WK or DE multiplied by EK, and /or this could be also BE multiplied by WK that you might add over here. Okay, WK itself may be stochastic or may be deterministic, and you may also have a noise term, and the noise term, this is measurement noise, is going to be mu k. The measurement noise is going to be Gaussian white. Okay, however, WK could be white, could be stationary. A stationary noise would be a white noise or a colored noise, or it could be non-stationary. And most common non-stationary noise that we use is an integrating white noise. We will need to have a non-stationary noise sequence if we need to get rid of offsets. Okay, and that is whether we use a state noise as shown over here, whether we use a state noise or we use a load disturbance or an output load disturbance as shown over here. The models could be either linear or non-linear in nature, and so what do we mean about that? So what I'm showing up here over here is a linear model, but the model could be non-linear also, and a non-linear model will be of the form xk plus 1 equal to fxk, f of xk, uk, dk. Okay, this is the way a non-linear model would be, and we might have yk equal to g of xk. Okay, and there might even be wk. Okay, now our matrix A is going to be nothing but partial differential of f with respect to x calculated at some value, let's say xk uk dk, and that will be our ak. Our bk is going to be df by du at xk uk dk, and we will have bdk is dou f by dou d calculated at xk uk dk. Okay, if we calculate it at a particular trajectory, then which means at point k plus 1, k plus 2, etc., we are going to have a time varying linear MPC. Most of the time, what we develop is a static linear MPC. And how do we do that? Is instead of doing linearization at time k, we instead do a linearization at steady state. Okay, what I mean by that is I will call this steady state value as with SS and with red color. So ASS will have a form like this, let's say. And BDSS. And you can have ASS, BSS, BDSS, CSS, and DESS replace the ABCD matrices at the top. Okay, so this is how you can use linear MPC. There's also a non-linear variant called non-linear MPC, as well as a sequentially linearized variant, which is what I'm going to talk about in a few lectures from now. Okay, so now let us come to the important part, and that is the form of the model and the disturbance modeling. Okay, now based on our prior experience with DMC algorithm, the researchers in late 1980s and early 1990s, what they use is a form that is known as output load disturbance model. Okay, and this is very clearly represented by the typical block diagram that we have grown so used to in our undergrad. This is measured disturbance D, this is manipulated input U, okay, and this is our load disturbance or output disturbance, and this is going to be our output. Okay, this was what was very commonly used. Okay, now if this is our model, how do we get the overall model for the system? We are going to get this as xk plus 1 equal to axk plus buk plus BDDK. Okay, and how do you go from GPGD in this form A, B, and BD? We have covered this in week 4 of the course. Okay, and it's the same concepts, nothing different. Okay, you can treat in putting these structures together, you can treat disturbance D very similar to the way you treat additional inputs U. Okay, and we have gone over this. Okay, and YK is going to be nothing but CXK plus WK. Okay, now for getting rid of or for offset-free MPC, WK is treated as random walk type noise, or also known as integrating white noise sequence. So that is the genesis of how we started attacking problems like this. Okay, now one of the issues with using a load disturbance model is that you do not get any feed forward information. Why? Is because the load disturbance is acting right at the end. It does not go through any of the processes. Okay, and that was the reason why later on researchers came up with state or input disturbance model. Okay, and in case of state or input disturbance model, you have Okay, now this part does not change. It does not ever change. Why? Because this is a known part of the model. There might be errors in it in the sense that A may not be perfectly known, or A is linearization of an actual nonlinear plant, and therefore A, B and BD will never be accurate representation of the plant. While that is indeed possible, what we are saying is that this represents the part that does not really change. Now, what do we add over here? We would add BE WK. Okay, and this is an additive noise that adds to the state. Okay, and then you have YK equal to CXK. Okay, over here also W, to take care of model plant mismatch or unmeasured disturbances, needs to be of a random walk or integrating white noise type sequence. Random walk and integrating white noise, you can use the terms replaceably. They mean one and the same when it comes to the MPC algorithm. Okay, so this is the state or input disturbance model. Okay, now what is input disturbance model? In input disturbance model, our BE is nothing but B itself in input disturbance model. Okay, so what does that mean? It just means that the input disturbance model is going to look like this is when you have an input disturbance model. Okay, what is it that it's going to look like if you have a state disturbance model? You have a GD, GW, GP, this is where you have a more generic state disturbance model. Okay, so these are all the structures that you can all potentially use, and what is the recommendation? I will come to that in the rest of this video. Okay, but before we go to that, let's talk about objective function and constraints. I've already talked about the objective function. A few things to note about the objective function: that we have summation y minus, I will just use r transpose q y minus r. Okay, now this we can then represent this in the terms of, as we have always been writing, we can represent this thing in terms of yp k plus 1 at k transpose gamma y yp. Okay, where gamma y is just going to be q in the as the block diagonal elements. Okay, now there's no reason why q needs to be constant value throughout the horizon. Let's say you are very confident about the model right in the beginning, but the model error starts increasing as the time progresses. You can have larger q, that means larger confidence in the initial parts, and you can have lesser confidence in the later parts. So that's also possible. People do that all the time. Okay, and likewise you have plus summation delta u transpose r delta u, and same way about r as well. Okay, so that's about the objective function. The constraints, the inputs constraints are of the form u min less than equal to uk less than equal to u max. The input rate constraints are of the form delta u min less than equal to delta uk less than equal to delta u max. Okay, and we have y min less than equal to yk less than equal to y max. Okay, or actually I will write this as yk plus 1. Okay, now What do we do with respect to the first input constraints? We write uk plus uk equal to uk minus 1 plus delta uk, and therefore we can write this as u min minus uk minus 1 less than equal to delta uk less than equal to u max minus uk minus 1. Okay, we have done this before, and then we can write the first part as negative uk is less than equal to negative of u min minus uk minus 1, and we have done that in week number 5 of this course. This we will write this as two parts: delta uk less than equal to delta u min, okay, and minus delta uk less than equal to minus max. Okay, this is how we will write this. Okay, now yk plus 1 is going to be y min less than or equal to c times xk plus 1, and xk plus 1 is cx a buk plus bddk, okay, less than or equal to y max. Okay, and then we can determine, we can substitute, and we will be able to write in the appropriate form. I'll just rewrite this. Y max. Okay, so these are the objective functions and constraints. When you are using the MPC toolbox, you don't need to keep a track of all of this. What you need to supply to MPC toolbox is Q, R, U min and U max are input constraints, delta U min and delta U max are input rate constraints, and Y min and Y max are output constraints. Okay, so these are the various constraints that you will be requiring. Okay, now the state estimator that you are going to use is in MPC toolbox you use Kalman filter. Okay, and the Kalman filter, for Kalman filter you need to finally be able to write your model in terms of, let's say, zk plus 1. I'm just using z to distinguish it from x. Okay, so a bar Okay, this is the final form in which you should be able to write the Kalman filter. We have done all the state augmentations to ensure that the estimator equation gets into this form. Whether you are using Kalman filter, whether you are using an extended Kalman filter, or whether you are using a moving horizon estimator, what you need to do is to get the final system in a form that looks like this. And how do we do that? We have covered that in the previous two modules, the previous 2 weeks of this course. As a matter of fact, you have also done an assignment where you treated one particular noise as a white noise and did the estimation, and then you treated it as an integrating white noise and did the estimation, and you compared the two, and you could very clearly see the difference between treating something as a white noise and as integrating white noise. This is something that you have done a couple of weeks back. Okay, the moral of that story is that we need to ensure that we know structurally what the actual system represents, and convert the model of that system into a form that has additive Gaussian white noise sequences epsilon and nu, where A bar, B bar, BD bar and C bar are augmented matrices, which we have covered multiple times. As a matter of fact, if I remember correctly, the terms that we have used, and maybe it might be better to use those terms over here. I think we have used phi times zk, gamma times uk, gamma d times dk and psi times zk, and maybe we might have used psi times epsilon k, and if it is psi times epsilon k, then r1 is just going to be equal to psi multiplied by r epsilon multiplied by psi transpose. Okay, that's all that is. And how do you get that? Just by the definition of expectation operator, you'll be able to get this. Okay, this is how one would ensure that the state estimator is being done in the correct manner. Okay, so I've spoken about the options for disturbance model. We will just recap that. First one is an output disturbance model. The second one is state disturbance model. And or input disturbance model. And third one is both state plus output. Okay, so these are the options for the disturbance models, and we have looked at the block diagram representation of all the three. Okay, now you would be tempted to use both state and output disturbance model, but we need to have caution before we go ahead and add disturbances in a crazy manner. The other way, you would be tempted to add just output disturbance model, because that very nicely gels with the DMC algorithm that we talked about. And output disturbance model, of course, is typically a safe choice, but there are better choices, and those the state disturbance model indeed provides better choices with respect to performance, with respect to clarity of how we can think and design a controller. Output disturbance model is the most clear and the most straightforward one for all cases, with the exception of inferential control. We'll talk about inferential control in a couple of lectures later. Okay, now with all this background, let me now go on to talk about how do you guarantee offset-free MPC. Okay, I think by now it would be abundantly clear that in order to guarantee offset-free MPC, your model needs to know that there is a bias, okay, or a persistent noise, or a random walk type of a noise that needs correction. Okay, and we do that again, as it must have been abundantly clear in the last few slides, we do that using disturbance model. But how do we do this? Okay, so to get to that, let me talk about a little bit of theory, something that we have done in week 8 and week 9. We will recap it again. Okay, before that, why is it relevant? And again, we have gone over why is it relevant. Okay, in case of model plant mismatch, or MPM, or unmeasured disturbances. Okay, or what another case is in case of what is known as model drifts. Okay, so for example, let's say you have installed at your home, in the kitchen, you have installed a faucet today. 2 years later or 3 years later, you will see that there is a little bit of deposit in that faucet. There is a little bit of rusting or corrosion that might happen in the faucet, no matter how good quality of faucet it is. If you live in a place which has some amount of hard water, then you will have probably some amount of salt deposits that have gone into that faucet. Okay, and then again, faucet is much simpler than most of the industrial systems, and running water in the kitchen is much cleaner than some of the systems that the industrial automation handles. So because of continuous use at high temperature, high pressure, and so on, what happens is that the behavior of any equipment when it is new or when it is newly serviced, and when it is say 5 months, 6 months, 8 months, 10 months into commissioning, there is a difference between that performance. The model was built at time 0, so it was built with the perfect condition system in mind. But as this time goes on, the system drifts, and that drift is sometimes not accurately captured in the model. So what we mean by that is when you say xk plus 1 equal to axk plus buk plus bddk. Okay, I'm only talking about the known part of the model right now, but of course it's also valid to BE or DE part of the model and also to the matrix C. The problem is that A, B, BD may not be accurately known. Okay, that means the plant has value A plant, B plant and BD plant, whereas the model has the value A, B and BD. This is something that you are going to do in week 11's assignment. The BD part you have already done in week 6 assignment as well. Okay, these are something that you need to be able to do. Okay, now what happens when you have the plant that is originally a nonlinear plant? You have linearized it at one point. The linearized version is never an accurate representation of the true nonlinear plant, and therefore that is another place which leads to model plant mismatch. The third part is unmeasured disturbances. So for example, the performance of your water heater during winter, for example, if the winter outside temperature is 4 degrees, 5 degrees Celsius, then the water heater performs more poorly or will find it more difficult to raise the temperature of the water to say 60 degrees Celsius compared to in the summer when outside ambient is at 40 degrees Celsius. So it's easier for the water boiler to take the water from 40 to 60 degrees than it would be to take it from 4 to 60 degrees Celsius. And that part is the unmeasured disturbance part. Okay, or it may be measured, but it might be unmodeled. So when so better and better systems have lesser and lesser things that are unmeasured. So for example, if you have an expensive car, the climate control system in an expensive car is going to measure the outside temperature, measure the inside car temperature, and then determine how much cooling to use. Whereas if you don't have a climate control, if you are using a less expensive car, then you may not be actually measuring the outside temperature, and the outside temperature comes in as unmeasured disturbance. Okay, so in all these cases, the fact that model and plant are not exactly in sync is something that is important, and that is important to get rid of the offset, the steady state offset in control, also known as ensuring integral action, also technically correctly known as ensuring offset-free MPC. Okay, so how do we ensure offset-free MPC? In order to ensure offset-free MPC, let's also write down yk equal to cxk part. Okay, we need to add some kind of a disturbance. Okay, so we need to add an integrating noise over here, or we need to add an integrating noise over here. Okay, but to make it a little bit more general, what we will do is we will write this in terms of not eta k, not a simple integrating white noise, but we will have, let's say, BEWK and DEWK, where WK could simply be an integrating white noise, and in which case DE is equal to I, WI equal to eta, just reduces to the previous form that I had just shown. Okay, but let me talk about things in a more generic way, that we have WK as any kind of a non-stationary signal. Okay, so that is the form that we are going to use. Now, irrespective of form that we use, the theoretical results that we have developed, we can still make use of the theoretical results, and that is the reason why it was so important for us to establish the connection between linear quadratic control theory and the MPC. The MPC that we done, the DMC that we did in week number 5 and 6, we then tried to connect it to linear quadratic control that we did in week number 8, 9 and 10. And in week number 11, I tried to make connection with the DMC algorithm as well as the LQ control algorithm. Okay, now for stability of LQ control, what we mean is that we are able to get the L infinity uniquely, okay, and A minus BL infinity is stable, which means all its poles lie within the unit disk. Okay, what do we need in order to guarantee this? In order to guarantee this, we need that A and B must be controllable, and Q and R must be positive semi-definite. By sequence. Positive semi-definite. Okay, now what do we need for stability of Kalman filter? What do we mean by stability of Kalman filter? Is K infinity is and P infinity bar and K infinity bar can be obtained. The Riccati difference equation will converge. K infinity is unique and A minus Kc is stable. Okay, what we need for that? We need that A comma C must be observable and A comma R1 must be controllable. Okay, if not controllable, at the very least it should be stabilizing. Okay, so these are the requirements for stability of LQ control and stability of Kalman filter, and these become important when we go on to the augmentation approaches. Okay, so what does this imply for offset-free MPC? Now, what this implies for offset-free MPC is that now you have so this WK might be added over here, or it might be added in the state. It doesn't matter where it gets added. What is needed essentially is that, so if it gets added over here, you need to ensure that WK is going to make the overall system as controllable, which means that WK either directly or through X should be able to go and affect the Y, in which we believe that there is a need for ensuring offset-free tracking. Okay, that means whichever outputs we expect biases, those outputs should be affected by WK. Okay, and if it is in the terms of xk plus 1 equal to AXK plus BUK, okay, then what it means is that we'll now need to do disturbance modeling, and the disturbance model is xwk plus 1 equal to axwk plus bw epsilon k okay, and based on that we will have our zk is defined as xk xwk, and we will get zk plus 1 equal to phi zk plus gamma uk plus gamma D dk plus psi epsilon k. Okay, and the covariance is going to be R1. Okay, so if this is the structure, okay, what is needed is that our phi comma gamma should be controllable, phi comma R1 should be controllable, and then we have yk equal to psi zk, and the third thing is that psi comma phi should be observable. Okay, so it means two things. What does it mean? It means that the integrating white noise that we have added should be able to affect the outputs directly or indirectly. The second thing that it means is that the integrating white noise sequences that we don't know what those values are, those we should be able to estimate it using the estimator of our choice. Okay, these are the conditions that you need in order to guarantee this. Okay, keep in mind that the corollary of this is that the number of disturbance W that you can add, the maximum number of disturbance will be equal to the number of measurements that you have. The minimum number of disturbances will be equal to the number of control variables. All the examples that we have taken so far, the measured variables and control variables have been the same. Okay, if measured variables and the control variables are the same, then the size of W has to be equal to the size of output. It cannot be lesser, it cannot be higher. But if there are more measured variables than control variables, or if measured variables are different, for example, temperatures are measured and concentrations are controlled. This is the example that we have taken in previous week's assignment. If that's the example, then the temperatures should be such, so the W should be such that from the temperature measurements you should be able to estimate W, and they also should simultaneously satisfy the requirement that you should be able to have W being affecting the variables, that is concentrations, that you need to control. That means the A and gamma part of this should form a controllable set. Okay, so that is the implication for offset-free MPC. Okay, so with that I come to the end of this video. So this was a rather long video, but this was primarily recapping all the things that we have done from the last 2 weeks in order to guarantee good performance and a good design of MPC. All of this information is there in the MPC toolbox manual, and if you have solved a problem, assignment problem last week without maybe realizing it, you would have ensured that you have taken care of these particular issues in order to get offset-free MPC. Again, the MPC toolbox takes care of all of this for you. They basically order the outputs in the order of most important to least important, and keep adding integrating actions to one output at a time until the observability requirement gets violated. That's how the MPC toolbox works. So it does that job for you, but it's very important for you to know how this particular thing operates, so that for your problem of interest you will be able to guarantee offset-free control. Okay, so with that I come to the end of this lecture. Thanks for listening, and bye.